Okay, we're looking at problem 6 out of chapter 7, and this is also a composite problem using simple shapes. It does have two voided areas, so it's basically just a rectangle with two voided circles. Units on meters, so what we have is 1 meter over, 1 meter over, 3 between, 1 meter down, 2 up. And the radius of the two circles, which are holes, is a half of a meter. So in this one, just like any of these, you need to start out with the centroidal axis, YY and XX, or the X-bar distance. So if you run through the centroid issue on this one's pretty straightforward. You can see that that's just half of the total. But this one you have to use the centroidal method. So what I've done is gone ahead and calculated that coming from that origin, 1.442. So if you're not sure where those came from and you need to run those numbers, you should check those on your own. You have to do the centroid on that, okay, the centroid calculations. So we're going to use, again, parallel axis theorem on this, but then since we have void areas, we're going to have negative moment of inertia on some of these. So I will have to look at it that way. So we're going to go ahead and assign shapes, and I'm going to call this shape 1, shape 2, and shape 3, so we can deal with that. So let's go ahead, we'll set up our chart. We'll do the axis first. We're going to have shape, then we're going to have I, X, C, area, the D distance, AD squared, and then ultimately the IX value. So again, D is the distance in this direction. So that would be the distance from the centroidal axis of the composite to the centroidal axis of each shape respectively, okay? And so let's go ahead and we'll check out 1. So we've got shape 1 is the rectangle. So it's 1/12 the base times the height. Since we're looking at this guy, this is our base. So we have 5 times 3 cubed divided by 12. So it's 1/12 the base times the height cubed. And so again, that's going to be 5 times 3 cubed divided by 12. And what we get is 11.25. So the area on this is just going to be 5 times 3. That'll give us 15. So the distance on this would be the distance between this axis and the axis of this guy. So the axis coming this way would just be half of 3. So it's 1.5 up or 1.5 down. So the difference between 1.5 and this would be our D value. And that turns out, if we do the math, we get 0.058. Get a little crowded. So this then gets squared times the area, and that gives us 0.05. So we're going to take that and add it to that. So it's going to add just a tad bit, not much, because the axis is so close here. The D isn't separating much, so the parallel axis is not really helping you out. Okay, so we're going to look at shape 2. So shape 2 is a circle. So if you go back to chart 7.1, you'll notice that the circle's moment of inertia is pi r to the 4th divided by 4. Interestingly, the circle, it doesn't matter whether you're looking this way, this way, this way, or this way. So it'll turn out to be the same number in any direction. But this is a negative area, so it's going to be a negative moment of inertia. So we're going to consider this a negative 0.049. Area is pi r squared. That turns out to be 0.785. And that's also a voided area, so that's 0.785. Okay, crowded myself a little bit. So what we're going to have here for the D value is going to be 2 minus 1.42 442, because that's kind of, we're looking at the distance from here to here essentially, okay? So when we do that subtraction, we get 0.558. Okay, so we're going to have this squared times that, so that's going to give me a negative AD squared, 244. So when we sum those guys, we get a negative 0.293. So they're not subtracting that much, but they are. What that's saying is that taking away from the stiffness. This right now is as stiff as it gets. So by plugging those holes in there, you're making it less stiff is what's happening. So we're going to go ahead and take a look at 3. So 3 is exactly the same moment of inertia. Exactly the same area, because it's the same size circle. And it's actually got the same difference here. So we come up with this. So that squared times that is going to give me that again. And we're going to add those, and we get another 0.293. Oops. We're going to get a 293. So when we sum this, notice it just diminishes a little bit. And that's 714. This would be meters to the 4th. So this would be our IXX. Okay. So let's see what happens. I'm going to expand this out a little bit because I just kind of cheated myself a little. Space, shape, IYC, area, D, AD squared, and IY. So shape 1, 2, and 3. Shape 1. Now this case, the moment of inertia, we're looking in this direction. And so this is the base now, and this is the height. So it's 1/12 the base times the height cubed. So the base is 3, the height is 5. So 5 cubed times 3 divided by 12. Notice this should, as you should understand now, this is going to be a little bit stiffer. In fact, it's almost 3 times. So right now, this is telling us if we're going to load this shape, we're really going to get the best loading this way with the least. It's going to be more rigid this way. It's going to be more bendy this way. That's what that's saying. Okay, area doesn't matter which way you look at it, so the area is always going to be the same. So the D distance is the distance between the centroidal composite axis and this guy's, and they're sitting right on top of each other. So in this case, D goes to 0. Since D goes to 0, AD goes to 0. So this right here is the stiffest that this shape would be because the rest of these are going to be voids. Okay, so we look at circle 2. So again, we're looking this way, but with the moment of inertia circles, doesn't matter which way you look. So these numbers are going to be exactly the same. We're going to get negative 0.049. Same thing with the area, negative 0.785. Now D is the distance from that one to this, so it's just half of 3 since they're symmetric. So that's going to be 1.5 meters. So that's actually going to take away a lot more than the other one did, because we're going to square that, multiply it by that, and we get a negative 1.766. So when we add those two together negatively, we get a negative 1.815. So because of symmetry, everything's going to be the same on this side. First off, because of what's happening with a circle, your moment of inertia for that shape is that, and the area is also the same because again they have the same radius. So this also is 1.5 meters, so that's 1.5 meters squared times that gives me a negative 1.766. We add that to that, and we get a negative 1.815. When we sum that column, it diminishes it a bit. So that would be 6.2 meters to the fourth. This would be our, what we call the IYY. And so what this is saying now, this is about twice as stiff as it is this way. So loading it, if we load it this way or this way, it's going to be a little bit floppy. But if we load it this way, it's going to tend to be a little bit more rigid. And again, that's what you're really after when you're calculating moments of inertia. Not always practical, though, depending on how you're going to use a member. So you may be stuck with that, but that's what that's showing. And when you get into beam deflections, you're going to see where all of this comes into play. All right, that was problem 6.